The sound is working with the microphone? All good to go. So, glad we're here and good to start. Today I'll be starting with the first lecture, which will be a little bit of introduction. So I'll be talking to you about my background, as well as the structure of the course to give you a little bit of an idea what to expect in the coming fortnights. To start off with my own education, I started off as the first part of the puzzle studying biopharmaceutical sciences at Leiden University in the Netherlands. After doing that degree, I did an honors project on hyphenating capillary electrophoresis with mass spectrometry. And to make my capillary electrophoresis devices, I used a technique called wire imprinting, where we use a plastic device and push that with a press normally used to make IR tablets, push that in a bit of plastic. I then went to France to do an internship in industry, and I worked at the pharmaceutical company Technologies Servier that were willing to start using capillary electrophoresis for counter-ion analysis. After my undergrad, I moved to Delft University of Technology to do my PhD. My PhD was on the development of a miniaturized total analysis system for real-time monitoring of fermentation. And the PhD project was a collaboration between the Biotechnology Institute and the Electrical Engineering Institute. So that's where I kind of started moving away from just doing sciences to having a more technical focus in my work. And the TU, the Technical University, is kind of the equivalent here with the IITs. As part of my PhD, I got funding to access the microfabrication facilities at the IMM in Mainz, where I learned a lot about manufacturing of fluidic devices in polymers using the LIGA process. I also did a part of my PhD at the Institut de Microtechniek in Neuchâtel in Switzerland, and there I could get access to a clean room to do processing of glass devices myself. After completing my PhD, I got a stipend to access the global knowledge reservoir. So I was able to travel to Tasmania, all the way at the other side of the world, and I set up microfluidics research at the University of Tasmania. With a couple of highlights of things that I've done is develop a new injection method for capillary electrophoresis, which we will be seeing the commercial outcomes from this afternoon. I did some microreactor work for organic synthesis and started to develop some budget microfabrication, because I've had a long-term belief that microfluidics should be inclusive and accessible to all people, and not only those at the specky IIT facilities where there's a clean room available. So I've always been looking for ways to democratize access to microfabrication. After spending 7 years in the School of Chemistry, I made a significant move. I moved to the School of Medicine, which meant that my office moved by 50 meters, and I ended up from one planet in another, because the culture in the School of Medicine is very different to that in the School of Chemistry. So I thought it was an insignificant move, and it got me a permanent position, but it forced me to completely change my research, look at more pharmaceutical analogs, which as an analytical chemist is not hard, because instead of looking for explosives and inorganics, I started looking at therapeutic drug monitoring, bioprocess monitoring in fermentations, getting back to the roots of my PhD, and also did some neuroscience on a chip that will be showing up later in the course. Again, driven by the passion of democratizing microfabrication, around 2013, 3D printing became a little bit of a hype and a buzzword, and it started becoming accessible for private use. So we bought the first 3D printer from Kickstarter for a couple of $100, allowing to look at the feasibility of the use of 3D printing in microfluidics. And if you've looked at the course, we've got a couple of modules on 3D printing and microfluidics. So yes, that all worked. I then got an Alexander von Humboldt Fellowship, where I, for the first time, was introduced to Professor Malik. The first part of that fellowship I spent in Germany in Saarbrücken, which is a town on the French-Swiss border. And there I had the extreme privilege to be working with Professor Mans. And Professor Mans is the person that very first thought of the idea of doing chemistry on a microfabricated device. So I had a really good time there. The Alexander von Humboldt Foundation is really, really good for people with families. And because I had a family, my fellowship got extended into 2 one-year periods. And the second period of that, I worked at the microfluidic chip shop in Jena, which is the former east of Germany, where I learned some commercial aspects of microfluidics and did some work on writing application notes for droplet microfluidic systems. Then in 2017, at the end of my Alexander von Humboldt, I got an offer to become a professor at Deakin University, heading the smart sensing team, aiming to develop the new technologies for early detections of threats and disease. And those threats could be explosives, building on some of my earlier work that I'd started at in chemistry, but it could also be diseases like COVID or the presence of E. coli in water. My team there has got a strong focus on manufacturability. We've got great facilities, including 3D printers, injection molders, and CNC machines. So it's very much, we're part of the School of Engineering, and we've got a lot of engineering capability. But the applications that's where the chemist in me wakes up again, where we work on the use and development of aptamers. We do in-field testing for nucleic acids. We've modified some sample preparation protocols. I've got a collaboration with a couple of students working on electrochemical sensing, with thin film conducting polymer electrodes. And we've got some projects on cell and particle separation using the different forces that we'll be learning about at the microscale compared to microscale components. As part of being deputy director of my center, I also have a part of a job as a knowledge broker, which means that I try to bring people from different disciplines and academia, government and industry together, trying to identify the problems and find solutions together. And since December, I'm the faculty graduate research director, which means that I am I'm responsible for nearly 1,000 PhD students in our faculty. Those students are spread within Australia. Deakin University has got campuses in Melbourne. I'm based in Geelong. There will be a map a little bit later on. We've got students further down the coast at Warrnambool, but we also have students at IIT Madras, IIT Hyderabad, Manipal, and all of them, if they have a problem with their supervisor, it ends up with me. So I hope that all the students and the supervisors are nice and friendly to each other, because that makes my life a lot easier from the graduate research perspective, and I can spend more time focusing on my research. To have a little bit of an idea where I'm coming from, I put a map of Australia here on the slide, and so Australia is in size larger than India. Australia is 7.7 million square kilometers, whereas India is 3.3. The difference is the other way around when we look at the number of people. Because in India there's nearly 1.5 billion people, whereas in Australia there's only 27 million, which means that per individual we've got a lot more space around. If we zoom in a little bit and we look at Victoria, which is the state where I'm living, and compare that with Punjab. Punjab is just over 50,000 square kilometers, whereas Victoria is 277,000 square kilometers. So Victoria is a sizable state, if you think how long times take to drive, but there's only 7 million people living there. So again, the population density is much, much lower than what you see here around. And yeah, I love that the campus is relatively peaceful and quiet, and there's some green spaces. But when I go out and off in traffic, you just see all those people moving. I'm like, oh, how can life be so busy? So here we've got Melbourne, Deakin University, the Warren Ponds is the research campus where I'm based. It's here in Geelong, and I live about half an hour out in the middle of nowhere. Between every now and then we've got a kangaroo, but I'll show you some photos later. Just that so you know, I don't like talking a lot about me, but I know because I was born in the Netherlands, live in Australia, my accent is different. So if I speak about nothing important for the first hour, you all can tune into my accent and then we'll move on to the science. So see it as a little bit of a primer, and maybe it also allows a little bit of interaction later on. If we look at my research, if you've listened in a little bit, I'm not a chemist, but not quite a chemist. I'm a pharmacist, but not quite a pharmacist. I'm an engineer, but not really an engineer. I do a lot of everything, and I had to put something together for my head of school recently, and I thought it's actually the mismatch that we do in this course as well, because people ask me like, are you teaching chemistry? And I'm like, no. Are you teaching engineering? And I'm like, oh, they're an engineer, no. So I kind of put the different disciplines together. So there's a very strong engineering aspect where we look at fabrication and design. So we'll be doing, I'm doing some 3D printing, some fluidic design, some simulations, look at how we can make the processes to make microfluidic devices, make that easier. So that's the manufacturability. And recognize that an instrument also needs to have a box around. The chemist in me likes developing the chemical assays, work on biochemical methods, see if we can find more in-field compatible strategies to lyse cells to get to the DNA. Look at see if we can use cell culture processes in droplet systems, and see how materials interface with the chemistry that's happening really nearby. There needs to be some innovation. That innovation could be in the application, it could be in the fabrication and design, and the materials. And the thing that I really like is that no one can do anything like that by themselves. So everything that I do is always as part of a team. And that means that you only get to really the added value of working as a team if you can trust each other, if you show gratitude to each other, if you recognize each other's contributions, and if you show respect. So it is really important to also implement the social aspects and have a good working team, because otherwise you're not getting to the points where you actually can get to the advantage of working across disciplinary boundaries. So getting back to my youth, I started at Leiden University. I already said it in the puzzle, where my project was free flow electrophoresis for affinity capillary electrophoresis mass spectrometry. And then I went to France to Technologie Servier. So looking on the map, I was born somewhere where the cursor is at the moment, in a place called Katwijk. Then it was a 20-minute bike ride to go to Leiden University, where I did my undergrad. And then just south of Paris, Paris is there, so Orléans must be there. I went 4 months to France to work there in industry at Technologie Servier. Really nice thing there is that they had my apartment next to the lab. So I worked with a capillary electrophoresis instrument with an autosampler. And if a vial would get stuck in the autosampler overnight, I could hear the machine crashing from my bed, but I couldn't get into the lab to fix it. So really good to be close to work, but you don't want your experiments going wrong. You don't want to hear that when you're working. I then did my PhD at Delft University of Technology, where I was the first one to do capillary electrophoresis on microfabricated devices with an integrated detector. So we used the processes borrowed from the MEMS industry to integrate electrodes either in contact with a solution or with a thin nanometer thick membrane separating the electrodes from the solution. And that way we could either through direct contact or contactless measure the conductivity of the solution above the electrodes, and that way characterize the different analytes. So these are a couple of the green ones are the ones working with conductivity detection. Then I worked with some electroosmotic pumping. That's work that we did in Switzerland. And after that I got a fellowship to go to the University of Tasmania in Australia. I started off as an analytical chemist in the Australian Centre for Research on Separation Science, where I continued with conductivity detection, but then tried to do that on chip with ion chromatography. And we started the 3D printing. And as pharmacologist in the School of Medicine, I initially taught pharmacology to the pharmacy students and later diversified to also teach pharmacology to the paramedics, people on the ambulances. So that was really good fun. To understand what they were doing, I was allowed to go along on the ambulance and actually see how they apply pharmacology in order to tailor their teaching. So I spent 2 days on the ambulance in Sydney, go and visit all kinds of accident scenes and see what the paramedics had to do and how that related to the drug, what was the knowledge that they needed to have to understand the patients, and what was the knowledge they needed to be able to prescribe some drugs. And surprisingly, the main motivation of the ambulance people was to prevent patients to vomit during transport because they didn't like cleaning the ambulance. So that was my big learning, that antiemetics was very important to any paramedic. Normal doctors and pharmacists didn't care. For the paramedics, that was the utmost important because they had to make sure that their van was nice and clean. So now at Deakin University, I'm in the School of Engineering, working on the development. So my research still focuses on the development of new technologies for early detection of threats and disease. And then I've got the knowledge brokering role in agricultural projects, where I talk with different contributors to the whole process from a research idea or an innovation all the way to implementation and extension, and try to keep that whole workflow going, trying to see where the pain points are and addressing that, and in that way helping to make communities in rural and regional Australia, make them more resilient for drought. So that includes some psychological aspects on working on themselves. It means diversification of crops. It means the use of different irrigation system. It means finding new ways to talk with banks and see what loans are available. So it's a very broad topic, trying to truly help the regional communities, because with global warming, no doubt we'll be heading for another big drought in Australia, and the communities need to be able to pull through that. And as already said, I'm the Director of Graduate Research, responsible for about 1,000 students. My home life. I'm married. I've got 3 kids, Steph, Bart and Manon. And the next slide have some photos of them on there. I also have 2 dogs. This is Murphy. Let's see if I can give it. So that's Murphy. He, a postdoc that left, couldn't take him with him, so we inherited him of a postdoc, and he's always happy. And then we've got Piper, who's a little bit more of a concerned dog, and in this time we've got some sheep and sometimes we've got lambs. So here we've got Piper being worried about one of the lambs that the mother didn't want to feed it, so a bottle-fed lamb. Here we've got my family. So I've got Steph is my eldest. He's both here and there. This is Steph's girlfriend, so she's not one of ours, but she's increasingly present in our household. Then we've got Bart. He's my middle son, and he loves nuclear physics and anything science, so I can kind of guess where he's going. He's 16 at the moment. And then we've got Manon, who's 14, finding her feet and also having a little bit of a knack for chemistry and mathematics. Steph doesn't. Steph is our social person in the household, and he's just started a degree in occupational therapy because he really likes helping people. So we've got a lot of people that like mathematics and science, and then we've got Steph that is a very sociable person that looks after people. Then I'm curious why you're here. So that was a lot of information about me. So I wondered if we could do a little tour to see who you are, what your background is, and what you would like to get out of this course, because I may be able to tailor it one way or the other. Could we start here in front?
Yeah, myself, Dr. Ritu Tandon. I have come all the way from Ludhiana, Punjab Agriculture University. I am a chemist there, but working more into the line of natural products, into isolations, derivatizations of the natural products. Presently, I am focusing on post-harvest domain. As far as the food packaging systems are concerned, food coatings for enhancing the shelf life of the coatings, and I'm looking for this course, as far as this course is concerned, smart sensing technologies, which can be applied to the food packaging systems in India. Another aspect of my working in at PAU, it's I'm looking after a quality control laboratory, which is presently NABL accredited for some of the aspects, like as far as the environmental concern is concerned, we are testing various food uh, systems for heavy metal toxicity, then pesticide residue toxicity, and that's what the another aspect is, providing nutritional labeling for the upcoming entrepreneurs, providing trainings to the upcoming entrepreneurs who are basically agricultural bachelors and want to pursue their own business, having their own land, having their own crops, fruits, vegetables. So that's all I'm dealing with presently.
Thank you. Yeah, Jati, you just go as well.
I'm Dr. Jitendra Singh Aulat. I'm working as assistant professor in chemistry department. Basically, I'm working on molecular imprinted polymers, and I want to learn about the miniaturization techniques that you are going to propose here.
Go.
I'm Dr. Sushila Rani from chemistry department. I'm assistant professor there. I have done my research work in analytical chemistry and pursuing work on the nanoparticle, and want to learn about the nanosensing and some techniques that you are providing.
I am Dr. Ajirmal. I am also working as assistant professor in chemistry department. Basically, I am organic chemist. My area of research is synthetic, organic and medicinal chemistry, and I research on synthesis of anti-diabetic drugs.
Myself Vikas Verma, I'm research scholar. I'm doing PhD in chemistry department on metal organic frameworks and layer double hydroxides. And I'm here just to know how chemistry can be applied on the micro fabricated device, just to explore. Thank you.
Thank you.
Myself Purnima Gasu. I'm from physics department and I'm doing my PhD in nanoscience and metal organic frameworks, basically material sciences. So I want to explore what kind of sessions you provide.
Thank you.
I am Rajesh Kumar. I am doing PhD under the supervision of Dr. Kumar Malik, and I am working on synthesis and application of MOVs.
Yeah. And you're coming for seconds.
I am Kirandeep Kaur. I am research scholar with Department of Chemistry. I am working on DPO-tactic solvents, basically extraction of phenolic compounds from plants using these solvents.
I am Gurpreet Kaur from chemistry department, Punjab University, Patiala. I am doing the PhD under the supervision of Dr. Jitendra Singh Holkar, and my work was on the layer double hydroxide synthesis and application.
Myself, Saurabh from chemistry department. I am here to know about the nanomaterial and other aspects.
My name is Safasi. I'm a student of chemistry department, and I'm here to learn about new techniques.
Myself Jayashree Kaushik. I'm from chemistry department and currently pursuing master's degree in chemistry honors with inorganic chemistry, and I am currently working under Dr. Jitendra Singh Holkar and doing a project with him. And right now I'm here to get some knowledge about nanoparticles and MIPs.
Myself Priya. I am a student of chemistry department. I work under Malik sir on the project of DP-tactic solvents. I am here to learn about something micro. Myself Diksha Garg, research scholar from Department of Biotechnology and Food Technology. I'm working on the development of sensors for the detection of meat freshness. I'm here to learn about the miniaturization techniques and the smart sensing.
I'm Manpreet. I'm research officer in EMRC, Educational Multimedia Research Center. I'm here to provide all the logistics support for this event.
I am Sandeep from computer center department. I am here for assist you about the live view on YouTube.
Thank you. So, thanks very much. I'm not regretting I don't have any nanoparticle synthesis in there, so I'll see if I can put it in later on, because there's a fair bit of work going on, and I've focused mainly on the analytical aspects and not that much on the synthetic. But it's good to know we've got so many people with nanomaterials, because I can always make some changes in the next week and then see how we can make that more accustomed. So, about this course, as I already said, it's very much the same way as that my research works, because it is all cross-disciplinary. So, part of the course we'll be starting off with the methods. So we're starting off very heavily focusing on analytical chemistry. I'll be giving a little bit of an introduction on why we'd like to take analytical chemistry into the field later on in the second lecture before lunch. We will, after a little expedition to look at 3D printers, you will be learning a lot more about HPLC mass spectrometry happening here in Patiala. Then we'll get a guest lecturer coming in to talk about some electrophoretic separations. And after that, we'll be start talking about microfabrication approaches, as well as the physics happening at the microscale. So we'll first get us all on the same page in terms of separation science. Then look how science changes when you go down to the microscale. What is the fluid dynamics happening there? How can you actually make the devices to do microfluidic experiments with? How can you get it to work for you? And then look at a range of different applications for DNA, protein analysis, or inorganics. So we'll be starting off from the basis in analytical chemistry, then learn about the fluidics and what's happening at the small scale and how do fluids behave, microfabrication, and then we'll go to the applications. I'm not going to be teaching by myself, and this week you'll have next week you'll be just with me, but this week we'll have a whole range of different people. So Professor Malik and Jetty will be teaching you HPLC mass spectrometry. Tomorrow you'll have the privilege to get a lecture from Professor Barraj Saini, who will be initially explaining 3D printing in the way that it's used. And then we will go to his facilities to have a look at the printers that are available here. And then Professor Subrit Baga will be coming over to talk about electrophoretic separations, how we can use electric fields to stack molecules really closely together so that we can enhance their concentration and therefore detect them more easily. The last thing I want to make sure, if anything is not clear, if I'm speaking too quickly, please stand up. We're here to learn a lot together. At no point, if you don't understand what I say, there's no point of either of us being here. So I can always try to speak slower. Probably works about half an hour, and then you have to tell me to slow down again. But please do so. Those of you that have seen me 2 years ago, just come and chat, say that, or if something is not clear in the lectures, either stick up your hand or come and see me afterwards. The best outcome we can get out of this is that all of us learn and have an enjoyable time, and that you're not falling asleep because it's all way over your head. So I've tried to reduce down a little bit of content to compare to last time, so that we all will be able to get on the same page. And then for the students here that want to do the examination, we'll probably have a small conversation again and not do a formal written test, because I think that through conversation you'll be able to show your learning a lot better than when we start doing a big written test and I need to mark all the exams. So we'll be looking at a recent article. I'll ask you a couple of questions about that, and then you will probably all pass the course. So if you've understood the general gist of an article on chemical analysis on a microfabricated device, that is the aim. And it is trying to get your brain to cross different disciplinary fields and sit on that engineering chemistry interface where we've got design aspects as well as others. So that was the introduction lecture. I'd suggest we take a 5-minute break or so where people can go to the bathroom, and then I'll start talking with the second lecture, which will be to start heading into the real content of the course. No one in need of a break? Then we'll just go ahead because we started late and I think we still want to have lunch at 1. So I'll see if we can shorten down this lecture a little bit because originally it was scheduled for 2 hours. And I think we have 1 hour left, which should be fine, yes. So we'll be doing. So in this lecture, the first part of the lecture series, we'll be talking about analytical chemistry. And analytical chemistry is the branch of chemistry focused on the identification, quantification, and characterization of the composition of substances, which could be solids, it could be liquids, it could be solutions. In analytical chemistry, we've got 2 types of techniques. We've got quantitative techniques, which determine what substances are present. It's the wrong way around. So we've got quantitative, which measures how much substance is present. And we've got the qualitative techniques, which determine which substances are present. So this should be crossover. That's what you get if you make your slides. So quantitative is how much there's there of each different individual substance. Qualitative is which substances are there, but not necessarily their concentration. And analytical chemistry includes spectroscopic techniques, separations techniques like chromatography and mass spectrometry that you'll be talking about tomorrow, and as well as electrochemical sensing methods. Analytical chemistry, we can do it anywhere. We can do it, typically we do analytical chemistry in a laboratory. So we've got an instrument sitting on the bench where there is an autosampler or an injection port. We can inject the sample into and we get the answers out. But sometimes that means that if we have a sample somewhere in the environment, it may take a long time before we get the answer of the chemical composition of that environmental sample. Because it needs, there's time required for the sample to be transported from the field to the laboratory for analysis. And during that time, the sample can degrade. There could be enzymes, there could be oxidation reactions going on. It may be hot in traffic, the car may not be air conditioned. So the sample may no longer have the same composition by the time it arrives in the laboratory for analysis as the composition that it had when the sample was taken. Also analytical instrumentation, it needs experts like Jetty to operate. So you can't just have everyone operating an LCMS. You need training, you need to be a specialist in order to operate them. It's complex procedures, but the good thing about that, there's a high level of quality, and that means that the answers, the analytical answers that come out are really reliable. So they meet regulatory frameworks. So if an accredited HPLC method said there is too much of a toxin in there, you can say you shouldn't be eating this food product anymore because the answer is 100% reliable and it will stand up in court. The other good thing about instrumental analysis happening in a laboratory that most of the time the same instrument can be applied to a wide selection of analytes. Typically with an HPLC run you can separate 10, 15, 20 different compounds and quantify all of them. So you don't need as many methods as you need instruments. And there's minimal impact of environmental factors. If it's very hot outside or very cold, your instrument is typically sitting in a laboratory under temperature controlled conditions, so the results will be the same all year through. If we want to do analytical chemistry in the field, the great advantage of that is we can do the analytical chemistry very close to the point where we take the sample, which means that there's no degradation and we can actually measure the composition of the sample as it is in the river or on site at the farm. It means that the sample will also have a higher level of integrity because there is hardly any time for the sample to degrade during transport. Typically, methods used for in-field testing are very simple to use. So you don't need a highly skilled operator to run the analysis, and there's even a growing group of chemical measurement systems that are available for citizen science. So you can buy a little paper card where there are some reagents deposited, and then there's groups of citizens that on a regular basis put a droplet of river water on that card and then take a photo with their mobile phone. If a certain I think it's phosphate and molybdenum. If there's a large amount of phosphate in the river, it will turn a certain shade of blue. They record that with a mobile phone, and the data, the semi-quantitative data, gets registered locally. But putting the droplet onto the card and taking the photo is something any citizen out in the world can do. So it's very simple. But because it's very simple and the people are not very well trained, in-field test methods rarely stand up for in court. So we get a good idea what's happening if there is 10 different citizen scientists measuring phosphate and 9 of them say phosphate is way too high. It's probably smart to get a river sample and get it to a normal laboratory for testing, because there's probably something wrong with the phosphate levels in that river. So it's a really good marker, but you need to have the validated laboratory results with your citizen science identification before you can start penalizing industries for polluting the rivers too much. Mostly the in-field tests are for a limited number of analytes. As I just already said, coulometric test is one example, and that's one specific reaction for one analyte being present. If you want to measure a whole suite of analytes, you need to have a whole range of coulometric agents deposited. In-field testing is very prone to environmental interferences. If it's a 12-degree day or 34, if you're a chemist, you know temperature affects kinetics. If you've got a coulometric reaction, your reaction times will all be a lot shorter at a hot day than they will be at a short day. On a hot and or cold and humid day, evaporation may not be an issue. But if you've got dry heat at 35 degrees, as it's at my place at the moment, if you want to do any chemical test in the backyard, the water that you're depositing on the paper is evaporated in no time. So environmental conditions, in-field testing is much more prone to the environmental tests. So in-field testing is nowhere near from new. And I found a nice image here for field chemical analysis of someone that put a timeline together. And the first reports of in-field chemical testing are actually 500 before Christ. So there has been a need for chemical testing outside the laboratory for a very long time. And the chemical test that has been so old is the testing of gold. What people used to do by then, according to the reports that were found, is that they'd use some very hard black stone, like slate, and they would make little traces on that with the gold that they found. Then also had gold standards from other known gold standards. So you can see here the different carats of gold, so 10, 18, 20, all there. So you put a scratch of your unknown gold sample, and then your 14, 10, 14, 18, 20, 22 carat, you put all lines on the black stone. Then there is a range of different etching solutions, and you wipe the little bit of the etching solution across, and there are different acid concentrations. So for testing the 10K, if you at the moment buy this same test as a kit, you swipe with a cotton bud a little bit of that etchant over the line. You can see here that the 10 carat has dissolved, the unknown hasn't dissolved, and none of the others have either. Then you go with increased strength of the acid and looking at what time your unknown etches away. And if your unknown etches away at the same time as the 14, but your 18 still remains, but it didn't etch away with the 10, it is likely that your unknown gold is around 14 carats, because the scratch that was put on the stone is of the same quality. So we think that in-field testing is all cool and we're new and we're using modern technology. This actually was already done 500 years before Christ. So people have known about etching rates, difficult, and done chemical assays out in the field or on markets for a very long time. A little bit later, or a long time later, Lavoisier was the next person that did a lot of chemical testing or reports that were found, or Courvoisier. And there was Antoine Courvoisier, who was the person that discovered that water consisted about not out of one atom but out of two, so oxygen and hydrogen. His wife Anne actually developed an instrument that was able to detect the consumption of oxygen by comparing the mass of inhaled and exhaled air. And here you can see a very complex instrument that was carried to a patient's bed. They measured the mass of the air before it was inhaled and after, and they could see that there was a loss of mass in the exhaled air compared to the inhaled air. And having already realized that oxygen is a separate compound, they figured out that actually during respiration oxygen is being used by people. And they could also demonstrate that if you'd get the person to exercise, they consumed more oxygen than when you had them sitting in a chair. So this was the portable instrument that they brought to the people's side in order to measure oxygen consumption. Then I think 1909 was the very first pH meter, but ion selective electrodes really became popular from the 40s, and there's been a lot of research going on since. So what's happening in an ion selective electrode is that we've got an ion selective membrane that allows some molecules to go through but not others. And if your target molecule manages to permeate the membrane, either through ion pair binding inside the membrane or by fitting through the pores, we'll be able to record a change in potential and therefore get a measurable signal. From 1906 indeed, when there was the first pH meter, there's a whole range of different membranes that have been developed. A lot of people here in nanomaterials. And at the moment, the ion selective electrodes are still rapidly developing and getting more and more advanced by getting new materials, composite materials, nanozymes, all sitting on the surface of these electrodes in order to evoke a response to convert chemical information into electronic information that we can store on a drive. Ion selective electrodes have been implemented about anywhere. So you can find ion selective electrodes that are used in agriculture, doing soil tests, industrial production to make sure that the processes are running okay, fisheries trying to measure ammonia in fish farms to make sure that the fish, but through their metabolism, don't kill each other, blood testing, trying to understand pollution levels, heavy metals, wastewater treatments, drinking water monitoring, and the production of cosmetics. So ion selective electrodes have found a manifold of applications, and there's still many more new electrodes being developed for specific applications. Problem is that the ion selective electrodes are typically developed for one analyte. So if you want to measure 5 or 6 different analytes, you'd need to have an array of electrodes in place. Connecting on the ion selective electrodes provide selectivity through the membrane that allows some molecules to come through. They're slightly different from the electrochemical sensors, which could be measuring the current or the voltage response as a result of the presence of a redox active compound. So we've got the amperometric and the voltammetric sensors, where the amperometric sensors measure the current caused by a redox reaction at a constant potential. So you know the analyte that you're after, you know the potential at which it oxidizes or reduces, and therefore by the height, the intensity, the height of the current, you can measure how much of that analyte is there. And for example, that is the mode of action of the glucose sensor that diabetic people would use. Voltammetry is slightly more complex. There you scan, you swipe a range of voltages, apply those to the electrode, and then you measure the change of current as a function of this increase or decrease of voltage. So you typically go up and then down again, and you get the curve. Voltammetric detection provides a lot more information about the kinetics, about how efficient the electron transfer is between your electrode surface and your redox active species. but it is a lot more complex to interpret and deconvolute the data. So very simple tests at home monitoring and perimetry, because we know when the glucose oxidase at what potential the signal will be forming. That's again the same figure copy-pasted, so these should be cross-referenced again. So we have analytical chemistry, looking at the different identifying, quantifying and characterizing the composition of substances. We have selectivity, that is an important part, which is the ability to measure one analyte in the presence of others. And for example, with ion selective electrodes, it's incredibly difficult to measure potassium in a background of sodium. And there's very few samples you can find where there's no sodium present. So selectivity is important, and then specificity is the ability of a method to measure the target with no interference from any others. An ion selective electrode is a selective detector, but selectivity can also be realized through a separation. And then you can separate your analytes, and that provides you specificity, and you then have a non-specific detector that knows by time when your analytes come by, and they can detect that separately. The last time here that we'll look at the timelines, because here we have gone to the portable instrumentations going to extraplanetary research. Here we've got a relatively old example, as old as I am, from a field portable instrument, and that is a gas chromatography system that has been sent to Mars to analyze chemical compounds there. So that's probably as far as chemical analysis has gone at this point in time. And in 1976, the first GCMS was sent to Mars to do the chemical analysis. And this was followed by a large system, the wet chemistry laboratory Phoenix. And Phoenix was originally intended to be sent to Mars in 2001. The voyage was then postponed to 2007. But here we can see a photo of the Phoenix, and what Phoenix had was a complex engineering setup where there was an actuator, kind of a scoop, to get some soil, a scoop of soil into a cup. That cup contained water and some reagents and a mechanism for stirring. After that, the soil could be filtered away and the liquid was filtered off. And then there was an array of chemical sensors, so an array of ion selective electrodes to measure a range of different inorganic ions. pH was measured, conductivity, some oxidation reduction potentials. For some heavy metals, there was a capability in the potentiostat to do anodic stripping voltammetry. There was chronopotentiometry for the determination of chloride, bromide and iodide. And they also did some cyclic voltammetry to analyzing to see if there were any reversible couples. So here we can see a picture of the Phoenix, and what this pretty much had was a robotic arm to put a scoop of soil into a beaker, wet it, filter, and then put it on an array of ion selective electrodes that then could do their assays, and that way chemical information could be transmitted from Mars back to Earth, which is where we're going next. So heading back to Earth is towards selective testing. Selective testing is pretty much when we only want to see the green apples. So in this instance, we may be able to put an optical filter over this picture and only pick up the 2 green apples and just ignore that the rest of them exist. And selective tests are really good for in-field testing because they're typically quite easy to operate. One of the popular examples of in-field testing or at-home testing or chemical testing that is done a fair bit is keeping the water in equilibrium in an aquarium. I'm not sure if anyone here has got a fish tank at home, but if you hold fish, fish tend to eat, and if fish eat, they poo. And if you don't have the right amount of plants in your aquarium, you quite quickly end up with too many nutrients. And nutrients means that the glass of your aquarium gets green, which means in first instance you can't see your pretty fish anymore. The next step is that all your fish are floating on their back, because they're deprived of oxygen. So it is important, if you like your fish and you want to keep your aquarium in as a pristine condition, as you can see here, is that you do the chemical testing. And the aquarium shop then sells chemical test strips that have a range of different colorimetric agents already deposited on them. And here you can see one of these strips. And if you put water into the test tube and you, for a couple of minutes, put the test strip into the water, your color will change. And based on the color intensity, you can get kind of a semi-quantitative reading of what the chemical balance of the key analytes in your aquarium looks like. And that may tell you that you either need to refresh some of the water, you may need to feed your fish a little bit less, you may need some more plants. But it gives you a fairly rich number of chemical indicators by having a simple test strip with colorimetric reagents prepared. And the great thing about this, the colorimetric reagents, the readouts, you don't need any smartphones or detectors. We can just read it out simply with the bare eye. The same thing happens with testing the chemical quality of a swimming pool. This is my swimming pool. We've just been able, last week it was officially opened and we could swim in it. We got it installed this summer. But in a swimming pool, it is quite important that you test your composition of your water as well, because you don't want your swimming pool to go green, nor do you want to get your skin get itchy once you get out of the swimming pool water. So then again, at home testing of the quality of your swimming water is important, because you don't always want to have to go to a shop or to a test laboratory. You just want to make sure on Saturday or Sunday morning your pool is still safe to swim. So like the aquarium test had the paper test strips, a lot of the pool test systems are actually you add some liquid colorimetric reagents, and then there's a built-in scale here for the different pH. So the pH 8.5 is pink, and then it goes to an orange for around pH 6. You add 2 reagents to this vial, and depending, the color will change depending on what the pH is. You can compare it with the orange to pink gradation on this window, and then you can say the pool pH should be around 7.6. If it's too pink, you may have to add some acid. If it's too orange, you may have to add some base. So you can do bucket chemistry in the backyard. But it's very good to have a chemical test at home that doesn't need it. The kit is very easy to use. You do 2 drops of one thing, 5 drops of the other, and it all works. So that's at-home testing with not really very bad consequences. Something doesn't work. There is also an industrial equivalent of in-field testing. I already said that spectrometry is very frequently used in chemical measurement and identification. There are really nice handheld spectrophotometers out on the market. So UV-vis spectrophotometers, handheld instrument, it looks like a kind of a large calculator. Typically you need to mix some reagents to get the colorimetric reaction to take place. You put your little test tube like a cuvette into the instrument, close the lid that sits on top, and then you get a chemical reading out in the field of what the concentration of your analyte was in there. And there's a large range of different colorimetric reagents for different analytes available that you can buy with the field portable spectrophotometer. There's X-ray fluorescence instruments available. You can see that there's an X-ray source that excites the fluorescence, particularly if there's certain metals present. And then there's the optics to collect the signal, where a photon counter detects the signal intensity, and then you can read it on the display. And the X-ray fluorescence is quite heavily used for testing if paints in old buildings could be still paints that contain lead or not. And then at that point it's quite easy if you can just take the instrument to the wall instead of having to take a bit of wall from your house to a laboratory to get it analyzed. Raman spectroscopy gives the chemical profile and is often used in chemical verification. Is this powder indeed a chemical used for industry, or could it be an illicit drug? So Raman verification, here you can see a Raman probe where a large white powder is identified based on its Raman fingerprint. So these spectroscopy instrumentation There's a range of different handheld application, which means that at customs or in case questions are for renovations, the answer is directly known and measures can be directly taken to depending on the outcome of the test. At home testing, not long ago we've done it all with COVID. So the lateral flow test is also a field portable test. Some test that was easy to execute and everybody could do at home. Unlike the PCR test where you needed to get your sample, get it sent off and then wait for, at least in Australia, in the early stage of COVID, it could take 4 or 5 days before you could actually get the text message from the PCR tests. When the lateral flow COVID test came out, you just do a test and without 10 minutes you know if you were COVID positive or not. Pretty much the same technology is also used in pregnancy tests. You have a sample pad where you have your sample mixed with some gold nanoparticles and a carrying buffer. There's 2 different lines. There's one line with an antibody for your analyte, and there's a control line. You can see here the analyte binds with a gold nanoparticle, gets bound here to the primary antibody, secondary antibody. If the analyte is present, we'll see the gold nanoparticle and therefore the purplish line here. Control line reacts to a reagent that's always present in the sample and confirms that all the mixing and that the test has worked well. If you get only your control line, it means that you're negative. If you get 2 lines coming out of your test, both show up, it means that you're positive. It doesn't tell you how long ago you got COVID, it's not quantitative, but it's a qualitative test. And for COVID, it was good enough to know you had it and you had to stay home. So they are all the specific tests, all designed to see one specific analyte, independent if that was the pH or the chloride in my swimming pool, or to see if I had any COVID antibodies in my nose. The next part of this lecture, I'll talk about separation-based assays. And here we can see a nice color-separated number of apples, where unlike the first picture that I showed you where all the apples were mixed up, here we can see we've got probably some Yona Golds or pink ladies, then some pink galas, then the green ones were the grannies, and you can see some other colored apples going to the back side. And if you've got your apples already sorted by color, you could use a universal detector, for example a balance, to measure how many of each of them you have. So you could say I've got 5 kilos of red apples and I've got 20 kilos of green apples. Can use exactly the same scales to measure the 5 and the 10 kilos because your apples have already been sorted, separated based on color. In analytical chemistry, we can also separate our molecules in separation science. And one of the ways that we'll be talking about tomorrow, you'll be learning about more, is chromatography. To keep everybody on the same page what the separation actually is, I really like the example of paper chromatography. In paper chromatography, we start off with having some ink started at the deposit line of a bit of paper. We then put paper in a jar that contains an eluent, which could be just water, it could be water, ethanol mixture, sometimes some ethyl acetate, so sometimes it's an organic solvent, sometimes it's just water. Through wicking forces, the water will slowly be drawn up to the paper and move up. And in that process of the waterfront moving up through the paper, the dye molecules in this paint drop will also move up. But there's some of these dyes that are better stuck to the paper than others. So if you've got a dye that actually is not stuck to the paper at all, perhaps because the paper is slightly anionic, an anionic molecule won't stick really well to the paper. So it will just be carried with the waterfront all the way on top. Whereas if you've got a cationic component in your dyes and your paper is mildly anionic, it forms an ion pair. So your cationic dye may actually be fairly stuck to the paper, which means that despite the force of the water dragging it up, it actually stays where it is and it moves very slowly. So after an amount of time, you can see here that the orange dye was really well stuck to the paper, the purple one not at all, and we can conclude that the black paint that we initially put on the paper consisted of at least 3 different compounds, and they're here separated based on how well they stick to the paper. Chromatography after the paper chromatography has gotten more advanced, so you'll all learn about HPLC later on. But in HPLC, pretty much you've got a pump and solvent rather than the bit of water that you put your paper strip in. Your sample can be loaded through a syringe, so you don't need to have your little circle drawn on the paper anymore. Then your zone of your sample is injected onto the HPLC column, where the well-retained, the compounds with a high affinity for your column will be moving very slowly through the column. The ones that don't have a lot of affinity will go really fast, which allows us then to get a detection trace where the ones that are coming out really quickly will get an early peak. The ones that come off your column late will get a later peak, which is better shown on the picture here. The signal from the detector is in HPLC what we call the chromatogram. We have the injection of our sample here. You can see that the sample separates here in 2 different compounds. You can see a part of the original sample. We've got the yellow compound that's not well retained, so it moves quickly through the column. And we've got the pink compound that's more retained. You can see here the detector first sees the yellow compound coming by because the detector is sitting here at the end of the column. So you can see nothing, nothing, nothing. Yes, the yellow one comes by. Then you pump more and more of your element through the column. And then yes, your pink analyte comes by. And that's the way you build your chromatogram. If we look at the advances in chemical instrumentation, because chromatography is a separation method, unlike all the selective detector methods that we've seen before, that could be easily field portable, separation instrumentation, bringing that out into the field, is a lot harder, and you need a lot of engineering to be involved. Instrumentation for in-field chemical analysis can be miniaturized or adapted in a whole range of different ways. Sometimes the instrumentation actually is not adapted at all, but just all mounted and bolted into a shipping container. So you can have a mobile laboratory, which means that you put your HPLC in a shipping container, you make sure it's well attached to the tables. If there's an environmental disaster somewhere that's happened, you can just put the shipping container there in place. They can measure every day, and once the disaster is over and everything is under control again, the whole chemical analysis laboratory can be moved again. So that's probably the lowest level of field portability. You just have a shipping container, you put it on the back of a truck. The next part that you can do is that you put a chemical separation instrument next to a wastewater site. This here, we'll be talking about that in a little bit more. This is a capillary electrophoresis instrument that is placed here at a water treatment plant in Australia. And it does every half an hour, it does a capillary electrophoresis run to look at the different nutrients. Then we come with the field loggable instrumentation, which is if you've got 2 strong men, you can bring it into the field. If you've got one tiny female doing the chemical analysis, there's no way the chemical testing can be done at the site of the sampling. Then we come with a truly portable instrumentation, where it's a small suitcase weighing 4 or 5 kilos, where the separation can be taking place in. And then we go to the handheld systems, which is where the microfluidic systems can come in, where you can have a handheld platform where still the complete separation, the complete assay takes place by miniaturizing the complete analytical workflow down into a very small scale. Just as some teasers on what's been happening in the field of miniaturization in chemistry. Most of you have a laboratory background. You would have seen a gas chromatography mass spectrometry instrument, which is typically about 1 meter of bench space. If you make your gas chromatography system by silicon micromachining, you can actually have something that's smaller than a shoebox that can still do the same separation by just miniaturizing down, having a shorter column. Because it's smaller, the heating, the temperature control gets easier. So with engineering, you can do the same gas chromatography separation in a very small box. Exactly the same trends have been done for liquid chromatography. So as we've seen earlier, in-field testing, there's been an in-field testing need for a very long time. In-field testing was done 500 before Christ. So 1980s, there were the first ideas where people thought, we're developing these great analytical separations in the lab. Wouldn't it be great to do it in the field? And here we've got big boxes on the plot here that I got from a Journal of Chromatography or JCA. Well, look at the DOI, one of those two papers. Here we've got the weight of the instrument and the time it was launched. And you can see that there's kind of a trend towards lighter portable instrumentation from between the 80s and now the 2020s. But here we've got a field portable liquid chromatography instrument weighing 42 kilos. Well, good luck if you have to get that up a mountain. But you can see that with smaller capillary columns coming in, microfluidic devices coming in for the columns, getting cheaper detection systems, because that's one of the things that is really important with miniaturization. We're not just miniaturizing the chemical assay, we need to miniaturize everything around it, because if we've got a miniaturized separation but we need a fluorescence microscope to do detection with, it's never going to be a field portable instrument unless we want to be at that 42 kilos. So the whole infrastructure that supports your assay needs to be shrunken down as well, which is why developments like deep UV LEDs are very important, because a UV LED is much, much smaller than a mercury lamp. So if you want to do UV detection with your LC, it is very important to have stable, high intensity, lightweight light sources available. Same thing, Vichy started developing their nanoflow pumping system, which again enabled the development of HPLC systems, because the assay hadn't changed, the separation didn't change, the column didn't change, but from having the large piston pumps, all of a sudden these Vichy pumps, the instrument could about half its weight, because these pumps were lightweight but still able to generate the pressure required to do reliable HPLC separations. So here the smallest weight now, around 2020, we have an article where a 2.7 kilo HPLC was presented. And a couple of years ago I went to an analytical conference, and there were indeed 4 or 5 different commercial suppliers selling little suitcases where you could get your HPLC to take anywhere. So we are progressing from in-field detection being only ion selective electrodes, because they're easy to use and portable, to the point that our analytical instrumentation starts becoming smaller and smaller, so we can actually do advanced chemical analysis in the field, which then gets us closer and closer to the data that can be held up in court if we do the testing only on site and not do the confirmatory analysis in the laboratory. I'll just ask, this was my original point where this was going to be the 2-hour lecture. Anyone that wants to have a quick break, or you want me to move ahead so we can go for lunch in 20 minutes scheduled? I'm happy to go either way, if anyone wants a quick break. No quick break? Gee, you get me working here. So we'll move on. And the second part here of the lecture where I broke up is where I'll be talking about field portable capillary electrophoresis and the chemistry engineering journey that we've been through, starting when I was still at the University of Tasmania. So here you can see, well, just first to declare, we had a patent that has been licensed by this company. So if they start making money, 1/10 of the revenue after all costs have been deducted and my university has taken its share may flow to me one day. So I'm biased. But it's still a very nice story to see as a scientist how actually your work can be adopted in the real world. Here you can see a beautiful photo taken, I think somewhere in New Zealand where the original testing was done. A nice waterfall. And here these 2 phone booths with the solar panel is actually a complete automated analytical workflow. We've got the back side of the phone booth. There's a little tube coming in. You can just see it here. No, that's a tree. Well, there should be a tube coming down here in the water where there is a peristaltic pump pumping up water from the river through a bit of paper where it's getting filtered, so the particulate matter is being removed. And after the filtration, it gets moved to the second phone booth. If I still got my mouse is here? Yeah, my mouse is gone here. So the second part of the phone booth here is an instrument for capillary electrophoresis. All this work started after home improvised explosive devices became a really popular way of attacking citizens. This here is a photo of the Twin Towers where we had the homemade explosives being used for the terrorist attack on the Twin Towers. Not long thereafter we had the Boston Marathon bombing. There was the bombings in Paris. There were a whole range of homemade explosives that were used for terrorist attacks. And that put a large demand on the analytical community. Because till then, large explosions and attacks like this had been done using professional high-end explosives. Your TNT-like materials. So all chemical testing for explosives was focusing on those at the target analyte. Unfortunately, your nitrate-based bombs can be made from inorganics, and there was no good analytical instrumentation to quickly screen for the presence of those perchlorate bombs, nitrate bombs, those kind of instrumentations. So we were in a team working on ion chromatography and capillary electrophoresis, seeing that these are actually analytes that by both techniques can be separated and detected really well. So we put ourselves the challenge in could we get a capillary electrophoresis method to a point that it could be used not by an analytical chemist trained to be working in a laboratory, but could we get the staff working at an airport doing or screening all the people? Would we be able to get a capillary electrophoresis instrument that is so easy to operate that anyone working in airport security can actually conduct a capillary electrophoresis separation? To answer that question, I probably first need to tell you a little bit about capillary electrophoresis. Here we have a setup where the separation in capillary electrophoresis, there we go, there's my mouse, takes place in a fused silica capillary, which is a glass tube with a polyimide coating around. The outer diameter is around 365 micrometers. The inner diameter of the capillary is typically around 50 micron. Your hair is about 100 micron. So the inner diameter, the liquid core where you do your separation in, is half a hair. So very small, near impossible to see with your eyes. What we do in capillary electrophoresis is that we do our separations in the electrolyte to make sure that we've got consistent pH. And all the way, I think tomorrow I'll be talking about capillary electrophoresis and what the ingredients are in this buffer. But what typically happens is that you fill your capillary with the background electrolyte, then you dip your capillary temporarily into the sample vial. You apply a little bit of pressure to hydrodynamically inject a small zone into your zone of your sample. So you exchange your vials, you do your injection, and you change your inlet of your capillary back to the buffer so that a small plug of your sample is surrounded by buffer at the front and the back. And then you switch on your high voltage power supply and you run your separation, where your analytes, your high mobility, fast moving ions will be coming past the detector first, and your slower migrating analytes will be coming by last. Engineering wise, this change of vials from your buffer to your sample back to your buffer is an engineering challenge. It's asking for maintenance, it's asking for a skilled operator to do repairs, and that is the bottleneck. If you want to do in-field instrumentation, you don't want to have a tray of glass vials moving around. So we had to find a way to get around that autosampler. We were doing a lot of microfluidics by then, and our pumps were always connected with the upchurch fittings. And playing around with these obtuse fittings, we had an idea like, couldn't we use one of these T-pieces and play around with the fluidics to simulate that walking around with the different vials, but then by using the liquid flows and not by changing any reservoirs anymore. So in the coming slides, I'm not a good artist, so this is what the crosspiece looks like made in PEEK, and a few silica capillary can go in here and they'll all meet here at the cross. I'll just visualize that with the cross that I can draw in PowerPoint. So what we did was to try to get this capillary electrophoresis separation going. So here we've got the same cross. Here we could have a tube coming in, a few silica capillary coming in with our buffer, one coming out to an outlet with a valve, and one coming out to go for the separation. And then we ground one of the outlets, so we don't have a fluidic outlet, but we've got a ground electrode in order to counterbalance the high voltage happening at the other side. So here we've got our system, where we've got our hydrodynamic flow of our buffer coming in. We've got our inlet capillary going into our T-piece. We've got our ground electrode with no fluidic outlet. And we've got our valve here with our wide bore capillary. So this would be a tubing with 200 micron internal diameter. And here we've got our separation capillary, which is 50 centimeters long and has got a 10 micron internal diameter. One of the things that we'll be talking about in more detail this afternoon, but there's a lot of similarity between, not sure why that's not showing pretty, but there's a lot of similarity between electrical circuits and fluidic circuits. And electrical resistances and fluidic resistances work exactly the same way, that if they're in series, you can add them up. If they're in parallel, you do 1 over the resistor, and you can still add up the resistors. So the way that current flows through an electronic system is the same way that liquids flow through a fluidic system. So the flow rate that we have inside a narrow bore tube is a function of the pressure difference, so atmospheric pressure at the end, the pressure that we apply at the start, the radius of our capillary to the power 4, and pi, and divided by the viscosity of the liquid and the length. And if we calculate that flow resistance of our 50 centimeter long 50 micron internal diameter capillary, or the much shorter 200 micron capillary, we can see that there's a 1.6 million difference in flow resistance, which means that we have no outlet here. If we pump in a liquid here, all of the liquid will go up, and there will be no liquid entering the capillary because the flow resistance is so high. However, if we then change the valve and we close the fluidic outlet here, then liquid is forced to go through the narrow bore capillary, and we can fill our capillary with background electrolyte. So we have not changed any vials, we've got the same inlet and outlet. We only have closed the valve and we can redirect the fluid. If we then introduce our sample, we can still introduce our sample with the valve open and it's going up. We close the valve again for a short period of time. This forces a very small amount of our sample into the separation capillary. We then open up the valve again and leave that small amount of sample sitting here at the start of our separation capillary. We, using some other valves at the other side, we introduce our background electrolyte again, and that goes up. So at this point, we've got exactly the same situation as we would have had after our exchange of vial. We've got our ground electrodes. We will have our high voltage electrode here in a little bit of time. We've got our background electrolyte in front and behind our analyte zone, and we've got a small amount of analyte introduced into our capillary for separation. So at that point, when we apply the potential difference, we can separate our analyte into the different zones. At the end of our separation capillary, we've got a universal detector. In this instance, this is a conductivity detector that can measure the different analytes coming by.
Which detector now?
Conductivity. So a capacitively coupled contactless conductivity detector. So this way, using 2 valves and 2 T-pieces, now 2 valves, 1 T-piece, 1 cross-piece, we were able to circumvent the way that we needed to exchange vials to order to inject in capillary electrophoresis. And all of a sudden, doing an injection in capillary electrophoresis was a matter of only switching on and off a couple of valves. So this then was commercialized by a company called Gray Innovation with an instrument developed to do testing at airports for homemade explosive devices. We started this journey in 2005. That was a couple of years after the Twin Towers had come down, and there was a lot of funding available and a lot of interest in in-field explosive detection. By the time we were finished and our method development for our separations were done in 2008, and after that the engineering team has taken this up on themselves in order to get a reliable instrument that could be used by a lay operator. So it was not, the difficulty of this project was not that much the chemistry. It is building an instrument that has got the robustness of being able to be implemented for airport screening. The product was ready in 2015, but that was when a lot of interest had decreased as well. So the instrument is commercially available. It has been screened by the US IATA, so it is ready to be implemented. And I think the only thing that's what we're waiting for is to have money available, which only unfortunately would happen in case that there would be another uprise in the use of homemade explosive devices. So at the moment that was put on hold. Company was really sad, but instead of just sitting down, they realized that the homemade explosive devices are technically actually the homemade from the same molecules as are molecules that are of environmental concern. Your nitrate, your phosphate. So we needed to change very little on the chemical separation method to make our explosive analyzer suitable to do nutrient monitoring. So the parent company started a second entity coming out. So there's now Grayscan, which is for the explosives. The same hardware has been lifted into a new instrument called eco detection. Same hardware, very, very similar separation method, and that's now being deployed for in-field and environmental monitoring. Don't get scared too quickly of this slide here. This is about a 1 month period of the Grayscan instrument running somewhere, and I'm not sure, this is either in a river in Tasmania or in New Zealand. We've had 2 different testing sites, and when I grabbed this off the eco detection website, it didn't indicate which one it was. So you can see here the different times that the measurements were taken by the instrument. We can see the nitrate concentration. Nitrite is not there, so very, very low. We can see the chloride. We can see the sulfate is moving here. We can see that if there's a dip in chloride, it corresponds with also a dip in sulfate. Where is the orangey one? That's probably the conductivity. So chloride, nitrate, nitrite, and fluoride. So fluoride we can see moving here. So every time this instrument takes a sample, it uses the fluidic process with the little crosspiece that I've just explained to you. That way introduces automatically, without any human intervention, it introduces a small sample plug into the fused silica capillary, then backfills, washes everything with background electrolyte, applies a potential difference in order to do an electrophoretic separation, and then the contactless conductivity detection measures the signal, and the time that the analyte comes past the detector is related with its chemical identity. So chloride is a very fast moving anion. So the fastest moving anion coming by will be chloride. If you run the system in reverse polarity, then your sodium is really fast. It's got a really high mobility. So instrument works in positive and negative polarity, which means that we can separate cations and anions, and then does a couple of other measurements. But importantly, it's coming with a bag of background electrolyte that can be operated for a month at a time without any human intervention. So this instrument is with its little solar panel, put somewhere in the field, drinks directly from the river. Because capillary electrophoresis, if you look at a 50 centimeter long, 10 micron internal diameter capillary, you can wash that with microliters of fluid. So if you only have a human infusion bag with half a liter of background electrolytes, that can actually last you 3 months of monitoring time, because you only need that little of your reagents and your sample per run to operate, and then still most of your liquids used are for washing the inside of the machine and not necessarily to run your separation. So we've got a new project with this company to start developing a fluorescence detector and some new reagents to start expanding the analyte sets from the current nutrient monitoring capability to get to more environmental contaminants. So if we look at the interface of in-field versus laboratory analysis, the big part of this lecture series will be talking about microfluidics and how great it is to do in-field testing. Please keep in mind that there's very, very little in-field testing that is reliable enough to hold up in court or in official decision making. So ideally, it is always matched with confirmatory analysis in the laboratory. The good thing about doing in-field testing, though, is that you can get an idea of what's going on, better than just looking or smelling at the paper, which means that you can work on informed decision making, and you may be able, through monitoring, to pick up accidental releases of toxins by industry. That's one of the nice things of this eco-detection instrument. At the moment, the Environmental Protection Agency has put for 2 different companies in Victoria, have mandated them to put one of these instruments in their water effluent, and that all the information is directly transmitted to the Environmental Protection Agency. Because they had the idea that always when we do an inspection that's planned, nothing is wrong. But we do know from looking at the environment that something is happening in the company, some activity, and then all the fish are belly up. So these companies are known to clean their waistline, not properly dispose of waste. So these companies have now been forced to always be monitoring their effluents, so that every 30 minutes or every hour, the complete chemical fingerprint, what's coming out of their factory, is being mapped. And whenever there's something that's out of the ordinary, someone gets a message on their mobile phone and they will come there to grab samples and do laboratory analysis. But this way, at least the EPA, the Environmental Protection Agency, knows when to come and to do testing, rather than to have people know that they're coming to testing and make sure there's nothing wrong. So having continuous monitoring in there and having the time-resolved chemical data is very important, to understand biological processes, environmental processes, but also to see what companies are pumping into the rivers. So be aware, there's no competition between field portable analysis and laboratory. Both have their application, but the focus of most of what I'll be talking about in the coming 2 weeks will be on these field deployable systems, going even a step smaller than I've discussed about now, but going to the nanoliter, picoliter volumes. Happy to answer any questions, and otherwise it's time to go for lunch. I see a lot of hungry faces that are desperate for lunch. Thank you very much. We'll be back at 2 for an introduction into the chip-based part and what's happening in our fluid dynamics if we go small. Thank you very much.